always unsteady, they're always three-dimensional, they are apparently random. They're not actually random, but they appear to us as random. And I will talk about it a little bit more in a few minutes, why I call turbulent flows as apparently random. They have a very large number of vortices. I hope some of you can associate, I mean, you are aware of the word vortices. I mean, it's kind of this kind of motion that you see here. It's not straight it's not along a straight line, it's along circular paths. So the flow fields are highly vortical with multiple length and time scales of motion. Multiple length and time scales of motion. And again, what these words actually mean, I will try to illustrate in the next few minutes. But these are the characterizing features of a turbulent flow, which may be there or may not be there in laminar flows, but they're always there in turbulent flows. Okay. Now, why we worry about turbulence? First, I showed you these examples. They are around us everywhere, and we worry about it because, first of all, it is fascinating. Well, these are my opinion. I mean, you may or may not agree with me, but I do believe that the turbulent flow is more fascinating, more appealing than laminar flow. And indeed, in the past, there have been painters and poets who have created pieces of art looking at turbulent flows. And I'll show you a couple of examples. Turbulence is useful. From an engineer's point of view, turbulence is useful. And I have put one example here. If you are trying to mix fuel with air inside an engine, you want the flow to be turbulent, right? Because turbulence can mix things together quickly. But at the same time, from an engineer's point of view, it is also undesirable. And I have given another example, which you see on the slide. If you have a turbulent flow past an aircraft, the drag increases, which is not a good news, right? You don't want high drag. So for that kind of application, outside an aircraft, if the flow is turbulent, undesirable. But in the same aircraft, inside its engine, you want the flow to be turbulent because you want more mixing. Okay, so it's kind of a mixed bag. Turbulence is not completely understood even today. This is one of the areas probably in across all branches of science, one of those areas which is not yet understood. We cannot claim we have understood everything about turbulence. Now the ironical part is, contrasting part is that it is not understood, but at the same time the equations that govern turbulent flows, that is known. So governing equations are known, and they are called the Navier-Stokes equation, right? Navier-Stokes equation. Students from mechanical department must have come across this, must have derived those equations. So the equations are known, and still it is not well understood. It sounds contradictory. Why is it like that? The reason it is like that, even though we know the equations, we have not been able to solve those equations for all kinds of flow fields. Does it make sense? I know the equation, but I am not able to solve. So if I am not able to solve, I do not have the solution. And I hope you will agree with me that knowing equations is not good enough. You need to get the solution to really understand that, right? So that is what the truth is. We don't know the solution. Now, when I say we don't know the solution, I mean to say for most flows of practical interest. Of course, there are some very simple flow fields with very simple geometry at low Reynolds number. Turbulent flows at low Reynolds number, very simple geometry, we have solutions. We have been able to get experimental data or direct numerical simulations. But then when I made that statement earlier that we do not know the solution, I meant for most flows of engineering interest which have very high Reynolds number. Okay. So because of these reasons, there is a lot of research effort that has that is going on that has gone into turbulence. Now, this aspect what I highlighted, that governing equations are known, but the solution is not known for high Reynolds number or flows of practical interest. Why is that? Why is that a contradiction existing, that equations known but we are not able to solve? And in my understanding, there are two reasons why we have not been able to get solutions for flows of practical interest. One is the chaotic nature of turbulence, chaotic nature. And the second is multiplicity of scales that turbulence displays. Now, the word chaos, or the adjective version of it, chaotic, is very often used by us in day-to-day language, right? We say if something is not organized, we say that it is chaos. For example, this is a very accurate statement to make that traffic in India, traffic on Indian streets is chaotic, right? We often use that word. It's total chaos, and that is true all over, everywhere. I'm coming from Delhi, even there I find it chaotic. Not so much in Imphala actually, because probably the traffic is not that much, but yeah. My point is that the way the word chaos is used, it does convey something what turbulence does, but to be precise, I should tell you what exactly chaos means from a mathematical perspective. I wonder how many of you have actually come across this statement. I don't know if you can read this. The resolution is not very clear. Can you read this? What is written here? You can? No? Okay. So I will read it for you. So there is a butterfly being shown. I hope that is clear. And there is butterfly effect written there. Have you heard about butterfly effect? No, you have not? Okay. So butterfly effect, that's the white statement in white text that is written. When a butterfly flaps its wings, it can actually cause a tornado. And to put it in more dramatic way, you see this picture. This picture is conveying that whether a tornado will develop in central North America next week or not, it may depend on whether a butterfly flaps its wings 5 times, or whether the same butterfly flaps its wings 10 times somewhere in the forest of Amazon today. Sounds out of the world. I mean, sounds very unscientific, right? Can a butterfly flapping its wing 5 or 10 times, can that make a difference of having or not having a tornado in Central America next week? Seems very unrealistic, right? Seems unscientific. But that is the truth. This can happen. And a system of equations, so what is the connection between, after all, a butterfly flapping its wings in Amazon forest and tornado? It's weather, right? Air, atmosphere, governed by Navier-Stokes, right? So the connection is that the Navier-Stokes equation is a chaotic system, and I'm talking from a mathematical perspective, not from my common everyday use of the word chaos. I'm talking about a mathematical system, chaotic system. What is a chaotic system? A chaotic system is one in which if you change the initial conditions by small amount, the outcome of that system may differ by a very large amount. Does it make sense? If I have a system in which I give input as 1.001 in my first experiment, in the second experiment I give the input as 1.002, a non-chaotic system, it will translate that much change in the output as what? First time the output may be 10.005, and the second time the output could be 10.006. That's a non-chaotic system. Small changes in input, small changes in output. Non-chaotic system. Contrast this with the chaotic system. Same small change in the input can make a huge difference in the output of the order. You made the change in input by 0.001, the output can become 2 times, 3 times, 4 times. That's a chaotic system. Navier-Stokes equation shows chaotic behavior at high Reynolds number, turbulent flow. And that is the reason why a butterfly flapping its wing 5 times or 10 times, after all, what change it will make? 5th decimal place, 6th decimal place in velocity, pressure. But that can eventually result into development of a tornado, or not the development of a tornado 1 week later. Okay. So the problem with this realization is that turbulent flows are unpredictable. Unpredictable in the sense that, look at the other figure that I have put here. What I am trying to show here is velocity versus time that you measure in a turbulent flow experiment. And I have put 2 curves here. One is black and the other is red. You see that? I am calling them 2 trials of the same experiment. Who did that experiment? I did that experiment in my lab. Now, when I am trying to do 2 trials of the experiment, my intent is to repeat the experiment. And if my intent is to repeat the experiment, what should I make sure? That the initial condition that I am putting, that should be identical in the 2 trials. I have done that. But realize that for any experimentalist in the world, when he tries to put initial conditions, there is always a limitation up to which he can reproduce those initial conditions. Why? Because he will measure his initial conditions using probes. You agree with me? Some probe will be there. So I set velocity to be 5.001 meter per second. My device or my probe can measure only 4 decimal places. I can make sure in trial 1 and 2 that the 4 decimal places are matching. I believe I have matched the initial conditions. But in nature, do you think there is no difference beyond the 4 decimal place in trial 1 and trial 2? There will always be difference. These are called perturbations. They are always present. So if there are perturbations beyond the decimal place which I can control, I will consider my initial conditions to be still identical, because I can't do better than this. But since turbulent flows represent chaotic system, that much perturbation at 5th, 6th, 7th decimal places which are not seen by me, in trial 1 and 2 will be enough to be amplified and make the difference that you see in the red curve and the black curve. Follow what I'm saying? Follow what I'm saying? I can always match the ICBC up to 5th decimal place, but beyond that, perturbations are always there, and because of that, turbulent flows will turn out to be different even if I match the initial condition. Is that a problem? Is that a problem for an engineer? It is a big problem. Because if you are doing an experiment and trying to get data and then design a system based on that, when your system, if that is an aircraft, it goes and flies, you thought that up to 5 decimal places, the actual conditions are matching your experiment, and that's why it should behave like the black curve. But what happens when it goes out to fly, beyond those 5 decimal places, there are always perturbations. It means that your black curve prediction will be useless because your aircraft will behave like the red curve shown there. That is called unpredictability. Chaotic systems are unpredictable despite you specifying the initial conditions to the best of your ability. Okay? Which leads to this idea that even if you do numerical simulations or do computations, that data will not be useful, at least in this manner. At least in this manner. Okay? The second problem, multiplicity of scales that I mentioned, what it means. If you look at the slide that I have, look at the figure that I have presented here, focus on the black curve. There are many curves that I have plotted there. Focus on the black curve. Look at the way there are many wiggles in the black curve. Wiggles means like this kind of a thing, right? Up and down, up and down. Do you see that in the black curve, there are one type of wiggles which happen like where my cursor is. Have a look at the slide. Do you see the cursor there? You see the wiggles that happen like this, where my cursor is. There is another type of wiggle that signal is showing, which is like this, where my cursor is moving. You see that? Right? What I'm trying to show here is that the black curve is actually made up of, it comprises of many sine or cosine waves with different wavelengths. You see that in the black curve? In the black curve, you see there is one wavelength which is I don't know, which is like this. See, one wavelength is going from here to here. This is one wavelength. There is another wavelength that goes from here to here. You see, that is also a sine wave. And then there is another wavelength that goes from here to here. Wavelengths, right? This is what I mean by multiplicity of scales. So if this black signal is the measured velocity from a turbulent flow field, I would say that at least there are 3 different length scales in the signal, or time scales if it is plotted versus time, velocity versus time. 3 different time scales. So since it has multiplicity of time scales, if I want to do a simulation in which I want to recover the black curve, and you have to choose, suppose you are doing measurements and you want to recover the black curve faithfully, what should be the capability of your probe? I mean capability in the sense that every probe can measure a smallest amount, right? Least count. It cannot measure something which is smaller than a given quantity, right? For any probe. What should be the least count of this black signal? Should it be a wavelength or time period I should use? Should it be this much time period? That should be the least count, going from here to here. Should it be like this, going from here to here, or should it be like this, smallest? So what should be the least count of the probe, the smallest time period or the largest time period? I may want any response? So your probe should be able to capture all time periods, right? That will be a faithful capturing of the signal. What should be the least count? Should be the smallest, right? Only when it has the smallest it can, if the least count is 1 second, it can capture a signal of 2 seconds also, but it cannot capture a signal of 0.5 seconds, right? So if your smallest scale in the flow field is very small, you need a very sophisticated probe. All right? Now it turns out that for turbulent flows, as the Reynolds number increases, the smallest time scale that you see in the flow field, or the smallest time period, will keep becoming smaller and smaller. And we do not have the technology yet to measure the smallest time scale of a velocity signal for a very high Reynolds number flow. Does it make sense? Having a probe with a small least count is sophistication. I mean, that's a more expensive probe or more exclusive probe. We do not have yet such sophisticated probes to capture the smallest time scale of a high Reynolds number flow, because that is very, very small. Same thing goes for numerical simulations. If you want to solve partial differential equations, the governing equations, if you want to capture the smallest scales, you need to have very, very fine resolution in your simulation. But if you want to put very fine resolution in your simulation, what will happen? The computational time will increase, right? It will require more computational resources. Again, we fail there because we do not have fast computers. Yet we do not have that fast computers to actually resolve all scales of motion that exist in a flow field like what I am showing here. So you do see these passenger aircrafts and fighter aircrafts are all flying, but believe me, we still do not have that fast computers in the world to resolve the turbulent flow field that exists on this even if you run allowed to run your computers for years together. We do not have, because the scales have become very, very small. Okay. So because of these two problems, one is the unpredictability and the other is the multiplicity of scales, I'm trying to explain to you that we do not have solution for most flows of engineering interest, and it is not completely understood. But then the question is that if we have not been able to understand all this, then after all, how have we been doing CFD? How have we been getting numerical solution of turbulent flows, and how have we designed such fascinating engineering system out there? And the answer lies in the fact that we have not tried to solve the exact governing equations of turbulent flows, but we have relied on modified versions of Navier-Stokes equation, modified versions. What are those modified versions? The modified versions are either a statistical form of Navier-Stokes equation or a filtered form of Navier-Stokes equation. Okay, statistical or filtered form of Navier-Stokes equation. So what we do is we first convert the exact governing equations to another form and then try to solve it. But the problem with that another form is that it has some new unclosed terms. Okay, and I will talk about that more in a little while. But before that, let me show you these modified, or the names of these modified equations, and I'm sure some of you would be familiar with at least some of these things what I'm showing on the slide. So when I say the modified or the filtered version of Navier-Stokes, first is Reynolds average Navier-Stokes, right? Rand's equation. That is one form of modified Navier-Stokes. And then I've also put on the slide what you actually solve for when you pursue these kinds of simulations. When you do Reynolds average Navier-Stokes, what you are looking for is not the instantaneous velocity, but what we call as the ensemble average of the initial instantaneous velocity. Ensemble average. So we are talking about statistics. Now going back to this figure, what I mean by ensemble average. So you remember I said I did the experiment 2 times and I'm getting different results. So what my quest as an engineer would be, and what actually Rand's or Reynolds average equation tries to solve is, it says that let me repeat this experiment not 2 times, not 10 times, but say 1,000,000 times. Okay? And then those 1,000,000 times when you do the experiments, in general you will get 1,000,000 curves like that, black, red, some other color, they will all be different. But how about if I take an average across that 1,000,000, right? Average across that 1,000,000, and then I get one unique plot, and I would say that I would design my system based on that average plot. I hope that makes some sense from the point of view of an engineer. All right? That's what Reynolds average Navier-Stokes tries to solve. Ensembled average of velocity, ensemble average of pressure. Okay? But for that, it doesn't actually perform the experiment 1,000,000 times, because that also is an impractical proposition. Who is going to do 1,000,000 times experiment? So what we do is we use that idea and convert the equation on paper into an averaged form and then try to solve it on a computer. But it will lead to a problem which I will highlight in a little bit. But that is what Reynolds average Navier-Stokes is. Now if you have a compressible flow, this idea of taking ensemble average, that is implemented in the form of what is called the Favre average Navier-Stokes. That's another statistical method for turbulent flow computations. Okay? First is Reynolds average, the second is Favre average. The third is what we call as the filtered Navier-Stokes equation. There is a third paradigm, third variety of modified Navier-Stokes. And here also there is one very popular example which is called large eddy simulation, LES. Some of you might have heard about this or maybe already using it. Now, large eddy simulation has been there for about 30-40 years. In recent times, people have done research and added more methods to this class, filtered Navier-Stokes, such as partially averaged Navier-Stokes and hybrid methods and so on. Okay, so it's either statistical or filtered. Now, what is filtered? Statistical, I explained it was a million averages. What is filtered? Filtered is, if you go back to this picture, I showed you 3 time scales which are present there, right? One is large, one is intermediate, the third one is very, very small. From a numerical point of view, which is the hardest one to capture? Smallest one. So what the filtered methods of turbulence do, they say that we will ignore the smallest ones. We will only try to capture or resolve the larger ones. Will that relieve the computational burden? Will that relieve the computational burden? It will, because it's the smallest one which is more difficult to capture. For that you have to make the time increment very small, wait for a long time for a computer to finish computation. So you say that we will ignore the smallest scales and we will only focus on the larger scales, which is like the filtered version of velocity. It is like this this analogy, you know, like you have on your music system nowadays we don't get that. Earlier we used to have this these controls. I'm forgetting the name of that control. Basically you can suppress a frequency, high frequency, suppress a low frequency and change the quality of music. Have you experienced something like that? Amplifier. Not amplifier, equalizer. It used to be called equalizer, and I think music composers still use it. People who compose music, you will see that they have this kind of a large device in which they push these buttons up and down. Have you observed this? Like A.R. Rahman and all, when they show their videos, they would do that. What are they doing? They are actually getting first they got the input from the singer, all the musicians, all the instrumental music, they have gathered as data, and then what they are doing, they at one point during one part of the song, they want the tabla sound to be more pronounced, right, rather than the flute. What do? They suppress the high frequency. Flute is high frequency, tabla is low frequency. So you will see more bass. I think that's what musicians call it. You amplify the bass and you suppress the sharp voices. At some other part of the song you want to do the other way, right? That's what we are doing here with turbulent signal. We are trying to keep the large time periods and removing the small time periods. Okay? High frequency we are getting rid of. Not because we are composing some music here, but because we do not have computational power to actually resolve those high frequency or low time periods. Okay, so that is the idea behind the filtered Navier-Stokes equation. And then lastly, I have put here another method which is not that popular among the community, but it is used in a very impactful manner for one class of flows, which is called for combustion problems, and that is called the Lagrangian probability density function methods. Now all these methods, what they are trying to do is to address the two challenges I mentioned earlier, but in the process they create a new problem. And that new problem is that the Navier-Stokes equation being a non-linear equation, when you do anything like this means what? Try to average it or try to filter it, it will give rise to new unknowns in the equation. Alright? Which was not there in the original Navier-Stokes. So original Navier-Stokes has 4 unknowns and 4 equations. Is it good news? From a mathematical point of view, if I have to solve for 5 unknowns, how many equations I need? 5 equations. So we call it mathematically closed set of equations. Navier-Stokes equation was mathematically closed, but we were not able to solve. So we modified the equation. But while modifying, what happens that the number of equations remain the same, the number of unknowns increase. We say that the mathematical closure has been lost. Alright? So that is the problem, which is actually called the turbulence modeling problem. Turbulence modeling problem. So in turbulence modeling problem, you basically have to address this, match this higher number of unknowns to a lower number of equations. I mean, basically you have to add more number of equations. So this exercise of actually fabricating new equations for these mathematically unclosed terms is called turbulence modeling, and there are some very popular models, and again I'm sure some of you are familiar with some of the models. K epsilon model, K omega model, some of you might have used, the shear stress transport model, SST. They are all those turbulence models which are trying to do what? They are trying to match the number of unknowns to the number of equations in the modified Navier-Stokes equation set. Okay. So now the question, so now we are talking about turbulence modeling. Now the question is, how do we get new equations to match the number of equations and unknowns? How do we get new turbulence models? Now, unfortunately, there is no natural law or exact method or theory that is known to us based on which I can arrive at a perfect turbulence closure model. There is nothing like that there. Okay. So how have we developed these models after all? A typical modeling approach is you investigate some simple flow fields and then you do observations on that simple flow fields at low Reynolds number. I call such flow fields as canonical flow fields, very basic flow fields. You can do numerical simulations using the original Navier-Stokes equation, and you can do experimental observations on them. You look at them and then you develop some understanding as a turbulence modeler, as a researcher in this area. You develop some insight, which is quite qualitative, to be very honest with you. It's like you observe something, you don't really understand everything, but simply because of the reason that you have looked at it for very long hours, if somebody asks you what it does, you will be able to tell a story, right? If there is a phenomenon that is happening about which you do not understand everything mathematically, but even if you simply observe it for a long time, you will be able to say something about that. Turbulence modeling, it may not sound very nice, but turbulence modeling, this area has relied on this approach. Observing these canonical flow fields and developing some insights based on that, and then trying to propose models. So these are the canonical flow fields I was talking about, having simple geometry and low Reynolds numbers, such as boundary layer, a turbulent boundary layer, very simple flow field. Another flow field is homogeneously shared turbulence. You just have two layers of velocity with some difference, and then you observe how turbulence behaves in that. Then there is this geometry with periodic boundary conditions on all the sides. So you have a cubic, you have a cube, your computational domain is a cube, you put periodic boundary condition on all sides and you simulate a turbulent flow field. This is also called box of turbulence, and also decaying isotropic turbulence. So these are the examples of simple flow fields. Now contrast those three figures on the top to the three figures that I have shown at the bottom. Now three figures at the bottom are representing real engineering flows. Flow past an aircraft, and this is some extension on the wing, the flow past around it, then a helicopter landing on a ship. All these are complicated flow fields. Now on one extreme you have these flow fields which you actually want to solve as an engineer, and on the other extreme you are considering these simple flow fields which are very different from this. But this has been the approach of turbulence modelers, to understand the flow field here, okay, and get some insight and then develop models which can actually be used for these kinds of flow fields. Now I don't know whether you appreciate it right away or not. This is a long shot. I mean, this is a tall demand to observe something in a flow field as simple as this. Based on that understanding, develop some models and expect them to work all right for such complicated flow fields. Okay, this is actually a very, very tall demand. I mean, it's not an easy task. And that is why any turbulence model you come across, no model is perfect. All models will have some shortcomings in some flow fields. So I can develop with much hard work, and over years I can use the insight and may be able to develop a model which is good for this kind of flow. But the moment I try to use that model for this kind of flow, will not do well. Okay? And that's why there are so many turbulence models out there, and none of them is perfect. Because this whole approach is, as I said, is a very tall demand. But this is the best we have been able to do. Okay? So I have taken a lot of time. I mean, you please let me know how much.
By 10:30 you have to come.
ठीक है, fine. So of course I have more slides, but I still want to kind of wind up.
By 10:30 you can come.
Yeah. So as I said, my intent was just to kind of make sure that the students find something interesting and hopefully inspiring. So I will not worry too much about showing you a lot of results, but kind of giving you some insights about turbulent flows. Now, going back to those canonical flow fields you see here, I said that we observe them and then we try to develop some insights. Now, traditionally, the way we have observed these flow fields is what we call as the Eulerian approach. Eulerian approach. What is Eulerian approach? Eulerian approach is like, in this room, there are so many people here, and after my talk, some of you may leave, some new people may come and sit here. Eulerian approach is, to illustrate, I would use this example, focusing on a location and recording, trying to understand what happens to that location. So I can choose one chair, say the second chair in the first, second chair from right in the first row there. I focus there and I just keep observing during this time who sat there, after this talk who sat there, and so on, and try to understand what happens in the room based on that. That's one approach. That's Eulerian approach. What is Lagrangian approach? Lagrangian approach is not worrying about that chair, but worrying about a person, what he is doing at different times. So identifying a person and tracking what he does all the time from 9:30 to 5 in the afternoon, and based on that trying to understand what has happened in this room. This is Lagrangian. So Eulerian is you keep the space fixed, do not worry who comes here. Lagrangian is you do not worry you worry about a particular person, but don't worry where he goes and sits. You see the difference? Eulerian and Lagrangian. Now, the analogy that I gave was chair and person. In fluid mechanics, what we will be talking about, location will remain location, but instead of a person, I will talk about fluid element. I have an identified fluid element. I track where it goes, what it does during all throughout the day. That is Lagrangian. Eulerian is I don't worry which fluid element is where, I just focus on one location and see what is happening. Alright, these are two different approaches. So I was saying that traditionally turbulence modeling has focused on Eulerian approach, because the data that your Navier-Stokes or the modified Navier-Stokes generates, I don't know if you have realized it by this time or not, it generates Eulerian data. It doesn't tell you what keeps happening to a fluid element, it tells you what is happening at a given location. Okay, so data is originally in the Eulerian form, and that's why investigations have taken place there. Now, in recent times, there is an alternate approach people have tried to follow, in which they follow the Lagrangian approach. Why do they follow the Lagrangian approach? Because their argument is that following Lagrangian approach is more intuitive, because all your conservation laws are actually Lagrangian in nature. I don't know if you have realized it by this time or not. You talk about Newton's second law, F equals ma. What is m? M is mass, given mass. Mass of given mass, in other words, mass of a particle. Particle is fixed. And then you say the acceleration of a particle is equal to the net force. You're not focusing on location, you are focusing on a particle. That is Lagrangian. You talk about laws of thermodynamics. You take this much gas, you add this much heat, then it does so much work, it is related in some way. But what is it about? Is it about a location or is it about an identified chunk of mass? It is about an identified chunk of mass. We call it a system, right? So that is also Lagrangian in nature. So the argument is that since our conservation laws are Lagrangian in nature rather than Eulerian, why don't we investigate turbulence physics following fluid elements rather than focusing on location? Okay? But then there is a challenge. The challenge is that if I am using Navier-Stokes equation, which is giving Eulerian database, how do I get Lagrangian data from that? To illustrate this, I want to draw your attention to this figure, this cartoon that I have made. You see these red circles there? I am denoting grid locations. When you do a numerical simulation, these are the grid locations. Right? If you want to do CFD of flow in this room, what you will do? You will create a grid. You will create a mesh. You will identify fixed locations where you will solve for velocity and pressure. They are fixed. That's Eulerian. That's Eulerian, right? So the data that I will get from such numerical simulation is Eulerian. I have data only at fixed points. But I want to follow fluid elements. So what I am going to do is, at a reference time t0, I will identify a fluid element for myself in that database, which is being shown as black dot here. Okay? And then using the local Eulerian velocity, I will track where that black dot goes. Right? So I've started following a fluid element. But then the problem is that at a later time, I mean at t equals 0, I can choose that fluid element to be coinciding with a node so that I have all the data from an Eulerian database. But at a later time, say t plus delta t, this fluid element would have moved to this location, the new black location. Right? What is the problem with that black location in the background of the grid that I have shown? Can you identify? What is the problem with this new location of the fluid element? So I'll just wind up, sir. Can you, any observations? What is the problem with that black dot compared to the red grid? Red dot is nowhere on the grid, right? Which means that Eulerian database will not give you any value at that time for that fluid element, because Eulerian data has data only at the red points or the red circles. Okay? To circumvent this problem, what we do is we actually interpolate the data between the grid points to get the value at that black location. Okay? That is called Lagrangian interpolation. Okay? And in that way we track the data. So this is the way we would track the data and then keep following that fluid element and keep recording whatever is happening to it and then try to understand what turbulence is doing that. So now given the time constraint, I'm not going to stretch it any further. I am just going to go directly to the I don't think I'll be able to give anything more than that. So what I'm going to do is I'm going to come to the conclusions, and it will conclude, of course, things which I didn't discuss, didn't get a chance. Lagrangian tracking of velocity gradients and the associated processes, as I claimed, reveal novel insights into turbulence physics. This is kind of a new area of research. Such understanding can aid in the development of improved turbulence closure models. I had a couple of examples to show, but couldn't get time. Specifically, I wanted to talk about how in our research group in IIT Delhi, we have recently identified the influence of compressibility on non-linear turbulence physics following fluid elements, following the Lagrangian approach. And specifically, we calculated what we call as the lifetime of various topologies, various flow patterns in a turbulent flow field. And in that research, we also showed how this new Lagrangian approach gives us, reveals physics and gives us data which is in line with the experimental observations, which the traditional Eulerian approach was not able to do. Okay, so these were like contributions from my research group in recent times. Yeah, with this I would like to end. I mean, it's a long talk already. I hope you did find at least some of the slides interesting. And if there are any questions, I would definitely willing to answer. Yes, please. Huh. Well, that statement which has made that an Amazon butterfly doing this and tornado, we do not have data to actually show that yes, there is on that day one butterfly flapped its wings and on the other day we had tornado. We don't have that much data, but we do have other chaotic systems for which you can actually generate data and verify this on a computer. It will not be Navier-Stokes, but we can have some mathematical system to show that the effect that we are talking about, that is true. I mean, you change the ICBC initial conditions by a small amount and it will result into large differences. So we can have data for a different chaotic system. But for talking specifically about that event, weather conditions, we do not have that much data. But then I do want to draw your attention to the fact that you go to any weather predicting website, there are many nowadays, okay? They will typically, if you go to like websites like weather.com, which are like more established, you go put a pin code, put Imphal pin code somewhere, it will show you weather, but it will show you weather for like next 2 weeks, okay? Day by day it will show. If you ask the person who is actually creating that database, what he will tell you that the farther you are from today, the uncertainty in his prediction is increasing. So even though today you are trying to check the weather of 5 days later, what is in Imphal, if you ask him how confident he is, he will say that he is far less confident about the day 5 prediction than tomorrow's prediction. You ask him why, he will say because it is a chaotic system. So even though they are trying to predict based on some statistics, the uncertainty keeps growing. Okay, so in that way, all weather prediction websites, all weather predicting authorities, they do know that the farther they go from today, the uncertainty increases. So in that way, you have an evidence related to weather. But yeah, coming back to the original thing, that statement, we do not have that much data to actually pinpoint that this butterfly made this tornado. No. But we have reasons to believe it is true. It can happen. Yeah. Yes. I know it sounds like when we say it, it sounds crazy actually. Hard to believe, especially for engineers and scientists. But there is truth in that. That's what chaotic systems are. Yeah. Yes, please.
Animals and birds can sense most of the things compared to human beings.
Sorry, could you?
Said about the
Butterfly effect?
Yeah. Animals and the birds can sense faster than human beings.
Can sense. Animals and birds can sense natural phenomena better than human beings. Yeah, I've also heard about this, especially when there is an earthquake. People say that dogs, they can sense it, and they kind of give warnings. Yeah, I also tend to agree with you, but I want to clarify that is very different from what we are talking about here. here what we are talking about is extreme dependence on initial and boundary conditions. So that butterfly, again going back to that butterfly in Amazon, mind you, that is not sensing something which is already there. See, when we say that a dog is able to sense a coming earthquake, probably what is happening, there are some vibrations in the earth layers, and maybe it is in the range that we are not able to hear, and the dog or the cat, they can hear, right? Probably that is happening. But what I am talking about, unpredictability, is not that. Here we are not trying to say that the butterfly knows somehow that a tornado is coming. We are saying something which is more profound than that, and probably that's why it disturbs people. We are saying that the butterfly is causing that tornado. You see the difference? A butterfly, a creature as benign, as weak as butterfly as we see, that has the power to create a tornado. That's what we are claiming. And as I said, this is more profound than a dog or a cat sensing that an earthquake is coming. Yeah. Yes, please. Huh. Yes, yes. Yes, at a given next time instant, yes.
Yeah. So how do we solve for that?
Yeah, so that's a very nice question. I want to clarify that this cartoon that I am showing here, here we are, when we are doing this exercise of tracking a fluid element, by that time the governing equations have already been solved. Solution is available to you. This step is a post-processing step. Post-processing step. Okay? So solution is available at all red rings, and now the problem is I have to find the value at the black point at t equals t. The way we will get that value is by interpolating the values. So suppose this grid point, this fluid element that I have shown here, it is surrounded by these grid points, right? So what we will do is, we will do a linear interpolation of this, and this, 4 neighboring values, grid points, to infer the value of the black point. Yes. So certainly there is some approximation involved, but we will try to make it as accurate as possible. That's how we do it. Yes, there is an approximation. Yeah. Oh, acha, theek hai. So we stop here. Okay. Thank you very much for your patient hearing.
Thank you, sir, for your valuable speech. So moving on, we have a keynote speech from Dr. Bharat Dahiya, from Professor Bharat Dahiya, Director, Research Center for Sustainable Development and Innovation, School of Global Studies, Thailand. So I would like to take a few minutes to introduce Professor Bharat Dahiya. Professor Bharat Dahiya is a social scientist and award-winning urbanist and regional planner. His research and professional work focus on sustainable urbanization, urban planning development, urban upgrading, sustainable and inclusive cities, urban environment, infrastructure and resilience, and urban governance. Professor has advised national and local government on policy matters and given them technical assistance. He also worked with World Bank, United Nations Habitat, Asian Development Bank, United Nations University Institute for Advanced Studies of Sustainability, and United Nations Development Program. Professor has made significant contributions in many reputed journals, and his most recent co-authored book, Partnering for Sustainable Development Guidelines for Multi-Stakeholder Partnership to Achieve the 2030 Agenda in Asia and the Pacific, and the Municipal Corporation of Ulaanbaatar honored him with a Medal of Honor for his contribution to sustainable urban development in Mongolia. And recently, he has held many academic positions, including adjunct faculty at the Asian Institute of Technology, senior advisor and visiting researcher at Chulalongkorn University in Thailand, visiting professor at the School of Government and Public Policy in Indonesia, and visiting research fellow at Curtin University in Australia. So may I now request Professor Bharat Dahiya to kindly deliver a keynote speech.
Hello, hello, can you hear me? Hello, hello, Would somebody I would like to extend my huge thanks to Professor Gautam Sutradhar, Director of the National Institute of Technology, Manipur. Working over the last 25 years or so in international development, I have played several international roles. Some of those were most kindly mentioned in the introduction. And I have been involved in several international projects, whether they relate to urban strategy, urban analysis, or international project development and implementation. At the same time, I have also been involved in knowledge production with international agencies like the World Bank, the UN Human Settlements Program, United Nations University, and also Metropolis. And I am series editor for the Springer book series, Advances in 21st Century Human Settlements. With this kind of background, and also advising the UN Habitat on the World Cities Report, I take a long-term and a wider perspective on addressing urban management problems around the world. So in context of that, I have created this PowerPoint for you, which focuses on three main things. First is, what are the two current questions on urban sustainability in the 21st century? Second is understanding the challenges of urban sustainability. And lastly, in terms of moving forward, what kind of agendas do we currently have, and what kind of strategies we may need to look at and adopt towards the future. I understand I have about 1 hour, and I will try to complete my presentation in about 45 minutes. So first of all, let's look at the two key questions which are facing the realm of urban sustainability in the 21st century. We of course live in the age of innovation and technology, and there is a rise of digitalization and innovation around the world. Also, we have just been through the disturbing global pandemic of COVID-19. And these, in addition to these, there is another big challenge that we face, which is of global sustainability. And the former UN Secretary General, Mr. Ban Ki-moon, said, "Our struggle for global sustainability will be won or lost in cities." We hear similar themes or messages from important international agencies and also academic institutions. For example, this Royal Institute of British Architects says cities are the global battleground for a sustainable future. A web page on the University of Melbourne talks about, without sustainable cities, global development goals will fail. So we need to understand why this is the situation. And it is the importance of such an agenda that the SDG 11 has been included in the 2030 Agenda for Sustainable Development, which focuses on making cities and human settlements inclusive, safe, resilient, and sustainable. And when we look at the latest, some of the two latest reports of SDGs, global reports, we get a snapshot of what is happening. For example, we find that the plight of slum dwellers has worsened due to the pandemic, and there are about 1 billion slum dwellers. Then we find that um, although 156 countries have developed national urban policies, but only half of them are in the process of implementing. Similarly, if we look at the latest SDG report for the year 2022, couple of these messages are re-emphasized with regard to the 1 billion slum dwellers. Also, it is said that in cities, about 86% of the municipal waste is collected, 82%, out of which 55% is properly managed. And these are some of the challenges that we find. In terms of the overall SDG progress in the region where India is, the Asia Pacific region, we see the progress from 2015 to 2021, and most of the targets are lagging behind, which is evident from these blue bars between the year 2015 and 2021. And in one or two cases, responsible consumption and production and climate action, actually the progress is backward or regressing. At the same time, when we prepared the first State of Asian Cities report at UN Habitat, we found that several challenges related to cities were existing at the same time in Asia. These were related to urban poverty, industrial production and related pollution, also increasing consumption, resulting in high greenhouse gas emissions and solid waste generation, as well as the impacts of climate change, which were related to the slow onset of examples like sea level rise and the increased frequency and intensity of natural disasters. So what we find when we look around in Asian cities, India included, that on one hand we have highly developed parts of cities, and on the other hand there are cities where, or parts of cities which look very undeveloped and not very healthy environments. And the question emerges naturally why this is so. Therefore, based on this background and introduction, the two key questions that emerge is why the struggle for global sustainability will be won or lost in cities, and why the conditions of affluence and squalor coexist in Asian cities. And these are the two questions that I would like to tackle in this presentation. And that is what we will do in terms of understanding the challenges of urban sustainability. Now, in 2007-8, the world reached about 50% urbanization, and which now stands about 56%. And according to the global mega trend of urbanization, we may reach 60% urbanization, which means 60% of the world population may be living in cities by 2030. If we look at the trend lines starting 1950, when the United Nations started to collect and compile data on cities and other data, we find that the trend lines are all going upward. These are from the different regions of the world, and you can see the Asia Pacific one, which has the brown line with square dots, and it is the one of the fastest growing regions in terms of urbanization. One pattern that we find here is that the size of cities is growing much bigger. Now, the two or several largest cities in the world are in Asia. Largest, of course, is Tokyo, and second largest city in the world is Delhi. And then there are, of course, Shanghai, Beijing, Mumbai, Bengaluru, and others, Kuala Lumpur, Manila, and Bangkok. So these are the big cities. And if we look towards the future, when I calculated this statistics for you, I found that 1.2 billion people will be added to Asian cities by 2050, from now until 2050. And if we divide this information, this data, by per year, we find that 34 million people will be added to cities in Asia every year. That is like 34 metropolitan cities, or maybe thousands of smaller cities. And that is exactly what is happening. When we are confronted with this kind of challenge, of course, what we try to do is we try to learn from what has happened in the past. And what we find is that some people have computed the number of years that it took to go from 10% urbanization level to 50% urbanization level, because it is mentioned that pre-industrial levels, before the Industrial Revolution, the average urbanization level was about 10% in Europe. So if we take that as a pre-industrial level of urbanization and going up to 50, how long does it take? So Latin America took 210 years, Europe 150, and North America about 105. And so these regions took so long because they had to invent and discover the technologies of Industrial Revolution, which powered the Industrial Revolution. Whereas if you look at the Asian region, as well as some countries within it, these geographical entities require lesser number of years to go from 10% to 50% urbanization, which means that there is faster technological progress, and that is because of the import of industry from the developed world of today. At the same time, if the industrialized countries of today, which we call the developed countries, if we look at their experience, how they managed the process of urban development as well as the process of urbanization, Bai and Imura, these two scholars, they examined and came up with a model called Urban Environmental Stage Model, in which they gave 4 stages of development with regard to cities and their environment. And if we look at these 4 stages in form of a diagram, this is how it looks like. So on the left is the stage 1, and the environmental impacts are on the vertical axis, and the horizontal axis is for time. So in the developed countries of today, there was a stage 1 when there were poverty related issues, and when those issues were of course existing in pre-industrial times, and when they were tackled, which means that the graph line comes down, then you have the parabolic line going up for the production related issues, which were related to the pollution coming out of industries, whether air, water, or land slash soil pollution. And when these issues were tackled by those countries, then they ended up in the current stage, which is stage 3, which is related to consumption. So currently that is where these developed countries are, and a fourth stage is awaited, which is called eco-city, and I'll be looking into all these different stages as we move forward. So this is how in paintings the industrial age is depicted. For example, this painting called Iron and Coal by William Bell Scott. And if we look at the pictures and paintings of the industrial age, this is how it used to look like. They were not the days of smartphone and photography, but people used to paint, or if they had time, they would also record some of these. And so this is how the industrialized Europe looked like during the Industrial Revolution. In some countries of today, that is how the world looked like, especially in developing countries. So this was a common sight, and that gave rise to the modern urban planning and management, the modern city as we know it. Of course, the railway supported this migration process of rural inhabitants or people who live in villages to cities, which was also depicted in the paintings of that time. And many of the cities in the Industrial Revolution time period, they ended up looking like how this picture depicts the condition. So, trying to understand the different stages, according to Bai and Imura, the first stage of development cycle is characterized by poverty, which involves issues like demographic growth and migration to cities from rural areas. There is high informal sector employment, which means people do not have formalized jobs because there is no industry or any developed tertiary sector. And there is lack of basic services like drinking water, inadequate sanitation, poor waste collection, and so on. And so if we look at the cities of Europe and North America at this time, this is how those cities look like. They look like many of the cities in Asia today. There were slums, and there was poverty, and there was disease. There were hospitals that were overloaded with people. This shows TB patients in a 19th century hospital. This was the condition in some of the cities which are part of developed countries of today. For example, can one guess where is these pictures from? In fact, they are from Paris in the 19th century. This is how waste was collected. And this one, you would see that on the left is a before picture, on the right is the after picture when the street has been cleaned from the garbage which is lying all over the place. And this was the condition in New York until the city government appointed a commissioner for street cleaning, which was thought to be an impossible task at that time. And so if we look at the developing countries of today, the cities especially, that is the kind of condition that many parts of these cities have. So they are undergoing stage 1 of development. And this has also been reflected in popular books like Planet of Slums, which use the slum data from the United Nations. So the question is, how do we understand slums? So slums used to be before understood as areas of poor living conditions and poverty and so on. But since the United Nations initiated the Millennium Development Goals, and SDGs are a follow-up of that, they came up with a quantitative definition focusing on household, because household is the unit which is used by national governments to collect data, like census, for example. And so, if a household, whether it is made up of one or more individuals, if they lack one of these amenities, whether durable housing, sufficient living area, access to improved water, access to improved sanitation, or secure land tenure, that household will be considered a slum household, and that is how the population is calculated. So one of the features of stage one is high levels of informal sector employment, and this is what you can see on the right side, which is called non-agricultural or urban employment, informal sector. And globally it stands at about 73%, which means 73% of people working in cities do not have formal jobs. Um, uh, and this is higher among women than men. And then in Asian countries, especially, I mean, it ranges from 10% in Singapore to shows you a little bit about this. There was also the characteristic of poor provision of water and sanitation. And the lower part of this graph focuses on urban areas. And you can see that many regions have population that are not properly covered by the safe drinking water supply. And this is more like a regional spread around the world. And similarly, this is a graph showing sanitation, although there has been progress between 2015 and 2020. That is what these graphs depict. But all these light green and yellow and orange shades show that these are the people who do not have individualized toilets in their homes. And this map shows a little bit of where these facilities are lacking. The red one is the areas that are highly lacking. Oranges are second level, second category, and the yellow one is like 70 to 99%, and green are more than 99%. And so as a result, if we put together this data, we find that in terms of percentage, about 24%, and this is the latest data from the World Cities Report, which came out last year, that about 24% of the world urban population lives in slums. So they are lacking one of the 5 amenities or more. And in terms of number of people, now we have a global challenge of about 1.059 billion people living in slums, which means poor quality living conditions. And if we look at this trajectory, we find that the number of slum dwellers has been growing. It stands at 1.05 right now, and some estimates show that this may go up to 2 billion, and which will be about 25% of the, actually it may be a little bit more than that. So that's about the stage one. Second stage is related to industrial pollution, and where the air pollution related to particulate matter or sulfur dioxide, which are the dangerous pollutants, they are in the air. Large quantities of industrial and hazardous waste that comes from the manufacturing process, and intense surface and groundwater pollution. Okay. So this is the stage one. stage 2. And here what we find is that now the developed countries have tackled that problem, but this remains a big problem in developing countries where the industrial discharge remains unmanaged, and most cities, because of various reasons, they are unable to build large-scale wastewater treatment facilities. And so the inhibiting factors are technical know-how, financial capacity of governments, lack of land in cities, and people's unwillingness to pay for the services. Okay. And then the other problem is related to water resources. So 1/6 of the Earth's population faces water shortage on a daily basis, and as high as 40% may face water deficit by 2030. And then there is the problem of water scarce cities, where the total groundwater withdrawals are greater than 40% of the annual water resources, and this problem exists in several regions. Other problem is related to air pollution, and the latest SDG report presents the data that 99% of the world's urban population breathe polluted air. That means almost everyone living on the planet is, breathing polluted air. That's quite a scary prospect. And 7 million people die because of premature deaths, and which is a huge figure because of respiratory diseases, and some of them may not be even reported. So this is a major challenge. The third challenge is related to consumption, and here what we find is large quantities of solid waste, and the growing garbage dumps around Asian cities, including in India, are an example of this, and increasing CO2 emissions. And so where do those things come from? For example, this is the problem of solid waste management, which is the most often cited problem by municipal governments, and they are unable to tackle it because of technical and financial capacity. The city governments do not know how to deal with this problem, and that has a lot of science, technology, and engineering implications. Then you have public transport, and 37% of the global cities have public transport, and out of those 37%, 51% of the residents have access. So, and this differs in different countries. So the first bar shows percentage of cities with public transport, and within them, how many people have really access who can go and take the public transport. So this also does not look very promising when it comes to developing countries. And there is a constant growth of motorized vehicles, which does not seem to stop, and it has almost become a status symbol to own. And what is happening is that as incomes grow and developing countries become richer, there is a copying of Western standards in terms of private vehicle ownership. And this graph shows that the passenger vehicle per 1,000 people in North America is about 445, the right axis. And if everyone in the world has car ownership at that level, there will be so many cars as depicted by these empty histograms. So even only in Asia Pacific, if the car ownership goes up to the American standards, the Asia Pacific will have more cars than the rest of the world put together. And so this is also a scary prospect. While some cities are trying to aim high and try to reach renewable electricity targets, still 84% of the global primary energy is coming from coal, oil, and gas, and 66% of that is consumed by cities around the world. So, in other words, what is happening in cities is that we need to move towards more renewable energy. At least we should accelerate the pace by which we will move towards that direction. And then on top of that, we have the challenge of climate crisis. And this is from the latest UN report, which is called the Physical Science Basis. And this shows several socioeconomic pathways where the world may be, which the world may be following. From fossil fuel development, if we don't do anything about it, we may have an average temperature of close to 5-degree temperature rise by the year 2100. And on the other edge of the spectrum is the sustainability scenario, where we will be, humanity as a whole will be able to restrict the average rise of the temperature to 1.5 degrees Celsius. That would be called a sustainability scenario. Already what we have seen is that many regions around the world have observed heavy precipitation, and the hexagons that you see here, 19 hexagons, these are the areas including South Asia and Southeast Asia, which have been observing higher levels of rainfall, more concentrated, not spread over time, but falling in shorter periods. So what is, if we compare this experience of developed countries with the Asian experience, what we find is that in the fast developing Asian region, these three stages are occurring simultaneously, not sequentially, which means that in the same city you have three types of problems together. And this Asian phenomena is unprecedented in human history. So what the cities in Asia are facing has not been faced by anyone else on our planet. And Bai and Imura argue that if a stage may not end unless the impact is felt and leads to public policy and action. So the impact has to be felt on so many different parameters for a collective and comprehensive action to take place. So to answer the question, why there is a tale of two cities in Asia is that there is an in-migration of labor-intensive and environmentally hazardous industries, which are mostly located in cities. And they are the ones that provide employment, and which leads to a faster pace of economic growth. And that's why there is a faster urbanization in the Asian cities. And the triple challenges of poverty, environmental pollution, and consumption are confronting these cities in a very short span of time. And right now, the model that Asian countries and Asian cities are following is grow first and clean up later. And this is the stage which is much awaited is a shift towards an eco-city, which is, according to Bai and Imura, can feed itself without relying on the countryside. Some may question that statement, and power itself with renewable energy, and that's still a long way to go to achieve that. And there may be efficient land use, composting, recycling, and reuse of materials, which will require more inventions in science and technology and engineering. And therefore, this eco-city of the future may have a smallest possible footprint with the lowest possible pollution. And I think this is the challenge that should be embraced by the institutes of technology, not only in India but around the world, to see how we can find these technologies or develop them so that we can try to tackle these ever-growing challenges um, which are confronting us. Moving to the last part of my presentation, uh, we are going to look at two parts. First is, what are the global policy agendas saying about sustainable and resilient urbanization? And then we look at a few strategies. So I'm sure you're familiar with the 2030 agenda, but it includes also the 5 Ps, which are people, planet, and prosperity, representing social, environmental, and economic issues. Along with that, we need to build partnerships to deal with all different kind of challenges. We have now realized in the 21st century that one institution cannot tackle all the problems. Um, Educational institute cannot tackle the problems alone. Governments cannot tackle them alone. Private sector and business cannot tackle them alone. And societies or organized civil societies cannot do that alone. So these different groups of stakeholders must come together and build partnership to tackle these challenges. The 5th P is the peace, which is the importance of which has been underlined by the current conflicts that we see around the world. And of course, all of this is reflected in uh, the package of SDGs that we are familiar with. Within the urban domain, there is an intergenerational policy agenda. It is developed for 20 years. The last and the latest one was agreed by all governments around the world in 2016, which focuses on 3 transformative commitments: social inclusion, prosperity, and environmentally sustainable, resilient urban development. That's what are the 3 big sustainable development issues. How do we achieve that? First is by building an urban governance structure, including those partnerships I just mentioned, and also to improve planning and management of urban development. That's what we are discussing right now. Of course, there are implications to all those other things that are mentioned as part of the 3 transformative commitments. And how do we achieve that? The achievement is going to happen when we have sufficient finances. That's why you see that national governments, including India, are investing a lot on smart cities and other dimensions of urban development. There is a huge drive to build capacity in city governments and other agencies. And there is a growing emphasis on developing innovations, technology, and startups that we see, development of different ecosystems. So if you want to understand a little bit more about this global agenda right now, I would suggest that you look at the World Cities Report of 2020, which underlines the value of sustainable urbanization. And it deals with economic, social, environmental, and intangible value. Intangible value is related to policy, planning, management, and so on. And perhaps one good news is that the UN declared earlier last year healthy environment as a human right. So that also inspires us to clean up the environment. Lastly, some practical strategies which we may use and which are not often talked about, but very briefly. It's not comprehensive. I'm just highlighting a few points given the limited time that we have for such discussions in conferences. So first is that this is the decade of action from 2021 to 2030 for achieving SDGs, and urgent actions are needed. So if we have to move forward towards that, I think we cannot overemphasize the importance of this. This is already understood. And then we need to revamp the urban management, and we have to tackle all these problems that I discussed, whether they are related to urban poverty or pollution, environmental management, consumption related issues, or which are related to the intangible value of urbanizations, things that we cannot hold in hand, but they matter a lot in terms of improving living conditions in cities. Another thing that has been missing, and some countries have been able to do, is community-led upgrading or development of cities, in which especially the people who live in slums or poor living conditions or informal settlements, as they are technically called, uh, there is much value of utilizing community action planning. And this is something that the planners, architects, designers, engineers have to become familiar with. It goes through community mobilization, and once they are mobilized, you organize them as community development councils, which are legally registered. Then you develop their capacity in addressing local issues. For example, in India, we have resident welfare association, but how can we make them better, and how can we create those in areas where the poorer people live, and then create community action plans working collaboratively between people, local governments, technical experts, and implement such partnerships. I would also like to underline the importance of higher education, including in science and technology and engineering. And so what we need to do is to equip the youth with relevant skills. There is so much more happening around the world that we need to learn from, whether future engineers, planners, architects, or designers. They have to be brought to speed with the bigger challenges in addition to the conventional education that we need to provide them. We need to update curriculums. And so with new models and experiences, maybe we need to do more international exchanges, learning from abroad, and sharing Indian practices with countries outside a nation. And also interdisciplinary learning. I think this has become very important now. Without this, you really can't move forward. Enrich and improve learning processes, whether they are studios or fieldwork, or I think NITs, institutions like NIT should work with local institutions, whether they are city governments or state governments, and see what are their challenges and how you can create labs to solve those emergent challenges that are available or they appear in the locations where these NITs are located. Then you have the very important point of documenting innovative and creative work. This is not only for our KPIs, which is key performance indicators, as academic institutions or whether they are other institutions, but so that other colleagues in India or beyond can also benefit from innovations and good work, and which might also inspire others. And therefore, and that is how we are going to move together faster towards achieving the goals. And so with that, I thank you for your kind attention, and thanks again for giving me this opportunity to share these thoughts with you. I think I have spoken about 45 minutes. If there are any questions, I'll be very happy to respond. I hope that you found this picture of cities and which are the places where demand for improved science, technology, engineering solutions is always there. Thank you once again.
Yes. So somebody is putting a question in chat box.
I'm awaiting your direction and advice.
One person is typing a question in chat box, sir.
Good afternoon. For some reason, I cannot hear anything.
Can you listen me, sir?
I'm not hearing anything. I see a raised hand from Icste. Okay, yes, Sham Babu, yes, you wrote a message. Yes, sure, we can collaborate. I see a message from Sham Babu from NIT, Manipur.
Thank you, sir.
Thank you, sir. Thank you, sir. Thank you, sir. Thank you, sir.
Very
Yes,
informative and nice presentation. And sparing your very well time.
Oh, thank you. I got the message that we thank you for your informative session, Professor. Thank you so much. I have received your message. Thank you.
Am I audible? Am I audible? Am I audible? Am I audible? Some echo. 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 Maybe due to WhatsApp and Webex. Webex. Yeah, I can disconnect. Yeah, I can disconnect and let help on Webex. Yeah, I can no. And let help on Webex. Yeah, I can no. And let help on Webex. Yeah, I can no. And let help on Webex. Yeah, I can 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 let help on Webex. Yeah, I can yeah, I can yeah, I can
Hello, sir. Am I audible to you, sir?
yes, you are fully audible, very clear. Yes, you are fully audible, very clear. Yes, you are fully audible, very clear. Yes, you are fully audible.
Once again, sir, please. Could you please speak, sir? No, sir, your voice is not coming. Sir, could you please speak again?
Sir, could you
Could you test it again, sir?
Yes. Can you hear me?
Voice is okay.
Can you hear me?
Yes, sir. Yes, sir. Yes, sir. You are audible, sir. Am I audible, sir?
Am I audible?
You are audible, sir. Am I audible to you?
Am I audible?
Yes, sir. You are audible. Am I audible to you, sir? Am I audible to you, sir? Am I audible to you,
Yes, I can hear.
sir? Am I audible
I
to
can
you,
hear you. Yes,
sir? Am I audible
I
to
can
you,
hear
sir?
you.
Fellow of IET UK. In Danfoss Power Electronics Global R&D Guest in Denmark, Dr. Sandeep Kumar Dwivedi has held the position of project leader and senior research scientist in the Drive Intelligence team since 2008. He is also advancing the understanding of green technologies and application in the commercial application for motor drives and power electronics. In the year 2016 to 2018, he was honored with adjunct professor at Curtin University, Perth, Australia. In addition to holding 7 worldwide patents and 2 engineering research books from Academic Press UK and IET Press, Dr. Sanjeev has written more than 40 scientific publications. In recognition of his master's degree of engineering, Dr. Sanjeev received a gold medal from Indian Institute of Technology in Roorkee in the year 1999, and also for his contribution to power electronics and drive. He received the IETE Bimal Bose Prize in 2017 and the Danfoss 9th Man of the Moon Global Innovation Award in 2015. So may I now request Dr. Sanjeev Kumar Dwivedi to kindly deliver the keynote speech. Over to you, sir.
Thank you very much. Thank you very much. Thank you very much. Thank you very much. Thank you. And engineering, which is Icste, organized by NIT Manipur, to give me opportunity for this keynote address. So this is my home place, and it is known as Kolding, and it is situated in middle of Denmark. And this is my workplace, Avo Fuel, where I'm currently working as technology manager. This company is, pioneer in green hydrogen technologies, and it is spread across the Europe. It owning the full value chain. From electrolyzer plant and before that renewable energy sources to distribution of hydrogen, and in the end owning the stationary hydrogen station and mobile hydrogen station. So we will, in this presentation, we will go through the green energy sources. We'll see how hydrogen is a unique energy storage element. Then we will deep dive what are the associated value chain of green hydrogen and why it is a new and reliable energy source from energy management perspective. We will touch upon power electronics, which is an enabler for the green hydrogen. So when we talk about contribution of power electronics in energy efficiency, in this cutting edge technologies where we are increasing the we're cutting the energy bill by sophisticated devices, kind of air conditioning, permanent magnet motor based drive, and LED based lighting and other things. And we see that this contribution of power electronics will continuously will support this green hydrogen journey. There will be I will give you a future trend perspective, and then we will have time for question and answer. So why green technologies? In 2015 Paris Agreement, nations around the world, they agreed about that rapid decarbonization is the need for current time. And later in 2018, this IPCC, Intergovernmental Panel on Climate Change, that reported the global warming of 1.5 degrees centigrade, which is shows that need to cut greenhouse gas emission. It is needed rapidly, and this emission need to curtail rapidly, even more urgent than what previously thought. And then this window of opportunity that is closing fast for any meaningful action, because if you are not reacting now, then it will be too late, and this will be irreversible, and our climate will face a great environmental loss, which cannot be maybe bring back to the original state. Policymaker has increased their effort to reduce the or to eliminate emission in all economic activities, and options that would deliver only partial emission reduction are not sufficient. So if you are talking about EVs and in transportation sector only, then it might be not a good idea, because there is it can curtail little emission, but it is not a solution. We need to think in a whole perspective. So it starts from the steel industry, it starts from the cement industry, it starts from the fertilizer industry, then aviation industry, marine sector, and then in all those sectors need to be decarbonized. And for this decarbonization, we need green technologies. And what are the green technologies and how they are contributing presently in India and globally, we will see later. So this full decarbonization of some industry and transport subsector is technically and economically challenging, especially on the heavy duty freight transfer and trucks, and where we consume most of our diesel and oil. So these sectors, we cannot change the sector to green energy sector, substituted by green energy driven, these trucks and heavy duty vehicles. So this is hard to abate sector, and the current number of solutions is limited, and then this is particularly technically and economically challenging sector is known as hard to abate sector. There is, however, a common solution from some of these hard to abate sector, and promisingly we see that hydrogen is a promising candidate, and we see that hydrogen produced with renewable energy, that is a definition for green hydrogen. That is a very good candidate, not only for the transportation sector on car and automobile, but also for heavy duty truck and hard to abate sector. And when hard to abate sector, then steel, cement, fertilizers, marine sector and aviation, all those are concerned. So green hydrogen can be used as, this also used as a feedstock for the production of chemical and e-fuel or directly as a fuel. So interestingly, when our Prime Minister last year declared that in a decade, India will be a hydrogen economy country, hydrogen-based economy country. And hydrogen-based economy country means we will be independent on the fossil fuels. So, and question comes in your mind that how it is possible? It is possible because India is leading in now refining the crude oil. and the technology used in the crude oil refining that can very easily, adjusted, or it can be tailor-made for green hydrogen based energy and energy supply and e-fuel energy supply. So we are having all infrastructure. We need large number of process engineers. We need large number of mechanical engineers. We need large number of chemical engineers, and this infrastructure is already we are having. We are leading. If you might know that we are buying the oil from Russia, we are processing it, and we are selling it to Europe and US in current time. So you know that what is our muscle power in the chemical sector, and this chemical sector muscle power can simply support us in the green hydrogen journey. So then it's only a question of just to break down the efficiency bar of electrolyzer. Like we need to keep that efficiency. We need to keep the efficiency more than 70% or maybe 80%, and then we need to have better distribution and storage techniques, and there already work is going on, and soon we will see that we will have a good infrastructure, and we will be able to use the green hydrogen as a feedstock for production of chemicals and e-fuel. So as I told you, why green hydrogen? There is an alarming issue on climate change. And as I stated you earlier, this very important phrase, the window of opportunity is closing fast for any meaningful action to limit the planet increase in temperature and to counter the global climate crisis, because it is irreversible. So we need to take action now. These are some data on green technologies and how renewable electricity generation worldwide. Then you can see that growth in and how the growth in renewable electricity generation. So you see that major portion is the hydropower station. So 61% renewable energy worldwide is coming from hydropower station, and then 20% is from wind, 8% from bioenergy, 10% from solar energy, and 1% from geothermal energy. And if you look on growth, then you will see that biggest growth is in the wind energy sector, that is 12.3%, and then you see that next one is the in total amount it is around 170 terawatt hour, but growth is in percentage, that is the second biggest. First one is on solar sector, that is 22.7%, and total contribution is 130 terawatt hour. And next one is that bioenergy, and next one is the hydro, and then last one green one is 5.9% is the bioenergy, and geothermal is limited to 2.5%, 2.8%. And these are some number which they simply state that renewable hydro accounted most of the renewable electricity generation, about 61%, 4,207 terawatt hour. And if you break down the bioenergy generation, because if we talk about green technologies, then this is one technology where we can get a lot of benefits. Not only we can maintain our environment, not only we can have clean water for industries and for people use, we can also generate some green energy from here. For example, in Denmark, cities like Aarhus, Aalborg, and Copenhagen, they are using all the wastewater, and they're treating this wastewater, and by treating this wastewater, they are getting the enough energy to heat local houses. And in terms of energy consumption, it is 100% energy neutral. So whatever energy needed for processing the wastewater, that is less than what energy they are getting by the wastewater byproduct. So we can aim a sustainable model for our country too in coming year, when our Prime Minister is focusing on cleaning the rivers, and then question comes in our mind, we are investing this huge amount of money in this infrastructure. How it help our country? It will help in terms of energy, green energy, as well as it will also provide us uh, clean water, which can be used by industry. And if some of you have heard already our transportation minister speech, you know that he's always claiming that he's selling so many crore rupees of water to Nagpur municipality and so many crore rupees of water to Mathura refinery and other places. So that is the reality, and we, you know, power electronics engineer and we power electronics fraternity has a big role here in this clean water technology, where aeration is needed, where compressors are needed, where variable speed drives are needed. So this technology is to tailor made whatever solution we are having within power electronics and drive, and how to integrate it with the water refining process, and we can transform the country. So these are some number, and you can see that bioenergy and this most of the things from wastewater treatment and this coming as a biogas or methane, and we can also convert these gases to biofuels also. So if we deep dive in renewable electricity generation by region, we can see that Asia is having big presence. You see that there are different, renewable energy sources. But if you see Africa, the terawatt hour, 140. I'm having 2019 data, 140 terawatt hour, where Asia is 1,812, and if you compare it, North America 693, and if you compare Europe 534. So the hydro plant renewable energy, contribution from Asia is biggest. Similarly, in wind, Europe is second and Asia is first. But please keep in mind that this contribution is mostly coming from China, as far as wind and hydro is concerned. But India is, keeping its momentum very high, and we are having a cumulative growth of around 16% or more than that, and our total energy generation around 50% is coming from renewable energy sources, and in coming 2 or 3 years it should be 60%. That is the goal for the power ministry. So we see that we are also coping up very fast, and other in solar you can see there is a clear lead by the Asia, 370 terawatt hour compared to North America and Europe. And please note that in solar, India, if you look on the top 10 facilities in terms of single staggered power generation, then out of 10, 3 of are very good. We are going in a good path in solar energy, as well as on wind energy also. We are ramping up quite fast. And geothermal, you see that North America and Asia, they are equal almost. And marine, it is a huge potential is there, but there is it is untapped yet. So being said that, out of these so many renewable energy sources or green technologies, why the green hydrogen? Because green hydrogen, it is, we see that by 2050, green hydrogen need to have a greater dimension than today. Reduce production reaching about 400 million ton, equivalent to 49 hexajoule. Why we need this number of green hydrogen? Because it is a fuel for future. We will deep dive in chemical properties and other volumetric property and gravimetric properties, but it is because of it is in a simple word, you can say that it is yesterday wind is today's fuel. You understand that yesterday wind means the wind which was yesterday or day before yesterday, that was tapped through wind power plant, and energy used in electrolyzer to convert water into hydrogen. So we are able to delink the wind with the energy. The previous wind, whatever the wind amount is circulated, that can be converted in a form of energy, and we can securely store it, transmit it, use it. And similarly, you can say that yesterday solar power, sunshine is converted for today's fuel. So this is the most important thing, is delinking of renewable energy, and then using it whenever it is needed. You can say that it is also possible with the battery, but you see that battery is having its depletion, battery is having its own associated cost, and battery, it, this is you know, you cannot, the weight and the volume and energy density, that is not comparable with the hydrogen. And on top of that, for all automobile, buses, marine sector, aviation, when it comes to the fueling experience, battery is having totally different profile, charging time of hour to many hour, and there is a limit where we can use the batteries, whether we can use it for heavy duty truck or whether we can use in the marine application. But hydrogen can be easily used in any vehicle, in any application, and even in the aviation and in marine sector, by converting hydrogen to either methane or to ammonia, or to convert it into e-fuel, other e-fuel, we can have almost the same experience what we are having with the present day fuel, and this carbon footprint is almost negligible. And if you are using the hydrogen as a gas, then there is no byproduct, and then only the water is coming out of it. So that's we are, we are going towards the close to the nature, and we are respecting our mother nature. What we are getting from mother nature, we are converting it to energy, and we are returning back in terms of water. So that is the power behind the green hydrogen, and that's why we see that already there are a lot of momentum around the globe, and there should be this momentum continuing for many more
Sir,
years, in coming more years.
sir,
I'm 11.
thought that it is not moving.
Yes,
Okay, continue, please.
yes. So there is something written, but I want to share my thoughts. So that's so then we see that electricity demand to produce hydrogen reaches close to 21,000 terawatt hour per year by 2050. This is the ARENA forecast. And achieving these ambitious numbers will be a major challenge. But as this report describes, this challenge can be met through a wide range of policies. There is policies in Europe, European Union already given a state directive that by 2030, 60% of their energy consumption in every farm should be by green hydrogen. And we have seen in this budget that the government of India already placed 18,000 crore rupees to piloting and to support early technology startup and early technology demonstration project, so that we can we can ride this journey. Still, for the sector to move from niche to mainstream, more diffuse policy and measure will be needed. Policymaker today can draw early lesson from the trailblazing countries. Particularly, when we say the trailblazing country, then this China is leading here in the green hydrogen. US is also trying hard, and now in Europe, full swing, we can see that a lot of work is going on. So it is predictable after geopolitical issue and pandemic, this Russia and Ukraine war and pandemic, that green hydrogen receive a new wave, and it is a reality now. An unprecedented number of report, news article, webinar, event last few years, they are touched upon this topic, and we see this impact nowadays. And each year around 120 million ton of hydrogen are produced globally. But this is mostly from the fossil gas and coal, which is a grey hydrogen, and which together account for 95% of global production. So please keep in mind that Everfuel has built their first electrolyzer plant for green hydrogen, and its first unit is 20 megawatt, and that is biggest in Europe operative electrolyzer. In next 2 years, it will be upgraded to 300 megawatt, and next 5 years, it will be to 1 gigawatt. So you see that there are electrolyzers plant, but very limited, and their power capacity is also limited. But there are a lot of projects which are working towards big capacity electrolyzer plant. Hydrogen used for crude oil refinery and for ammonia and methanol synthesis represent almost 75% of hydrogen consumption. So, and it doesn't matter if you are building ammonia from, you know, natural gas, converting natural gas to hydrogen, or from coal you are converting it to hydrogen, or you convert it from using the renewable electricity and converting using the green hydrogen for these refineries to convert hydrogen from ammonia and methanol. And when you convert green hydrogen to ammonia and methanol, then this is the e-fuel, or you say electrofuel. So we see that greenhouse gas emission. There is a if we want to reduce it, it is only possible with this green hydrogen journey. These are some interesting facts about hydrogen as energy storage element. We see that it is the lightest element in the universe. Its atomic weight is 1.00, and then it's not a radioactive, it is gas, and until minus 253 degrees centigrade, or this 13.81 degree Kelvin, it is in gaseous state, and its boiling point is around 20.28 degree Kelvin. This ionization potential is 13.598, and this is its electronics configuration. So here there is a definition of hydrogen. We know that green hydrogen is any renewable energy source, then it is the green hydrogen. Yellow hydrogen is when solar power electrolysis is done. Turquoise hydrogen when we are using methane pyrolysis for generating hydrogen. Blue one is we use a conventional, steam reformation method, but whatever the carbon dioxide produced, whatever the carbon is produced, that is captured and is stored. So if you capture the equivalent carbon produced during the steam reformation and you store it, and it is the blue hydrogen. And if it is a nuclear powered, then pink, and steam reformation gray, coal gasification brown, and black, depending on the which type of coal you use, lignite or anthracite. So depending on that, this color is changed. And these are some application and some short notes about it. We will not go into detail. So if we look on hydrogen as a energy storage element, then you will find that energy density megajoule per kg of hydrogen is 141.8, and liquid is same, while methane is 55.7 and gasoline or petrol is 44.4. So megajoule per kg energy density of hydrogen is highest, and energy density megajoule per liter, then you see it is quite poor. So, and specific gravity. So if you see that it is very light, 0.071, and boiling point is minus 250 as I told you, and CO2 emission is 0. And flash point, there is no flash point in hydrogen as compared to gasoline or petrol 13.3. So please note that when we say that hydrogen, the only advantage is energy density in terms of megajoule per kg. But if you talk about liquid, megajoule per liter, that is not good. Or volume basis, megajoule per meter cube, that is also not good. So on weight basis, hydrogen has a high energy density, around 3 times greater than the most fossil fuel. Hydrogen has a very low boiling point, and then liquefied hydrogen is currently used in special application, such as space mission. In such cases, issues to do with thermodynamic efficiency are not critical. However, they became a serious concern when hydrogen is being considered for a mass market fuel. So as I stated earlier, the specific gravity of the liquid is low. Hence, its energy density on a volume basis is only a third of value of gasoline and other liquid fuel. In round number, a tank of liquid hydrogen delivers only a third of energy of a tank of gasoline. This low specific gravity negates the effect of having high energy density on a weight basis. So you see that there is a high energy density on weight basis. So if you say 1 kg of hydrogen compared to 1 kg of petrol, that having 3 times more energy density. But from volume basis, so if you compare a 1 liter of hydrogen in liquid form compared to petrol or diesel, then it's only 1/3. So all in all, it is equivalent. Hydrogen has wide flammability limit and low minimum ignition energy. These properties create safety concern and issue that need to be considered. The fact that hydrogen does not emit CO2 does not mean that it has no greenhouse impact. When burned in air, this gas creates nitrogen oxide, and some of which are potent greenhouse gases. So this volumetric energy density of gaseous hydrogen at atmospheric pressure is 0.09 kg per meter cube. Consequently, under normal condition, much space is required to store gaseous hydrogen. Therefore, hydrogen is virtually not stored or transported in gaseous form at atmospheric pressure because it is simply not efficient. At a pressure of 350 bar, the volumetric energy density of gaseous hydrogen is 26.1 kg per meter cube. You see, 0.09 kg per meter cube to 26.1 kg meter cube at 350 bar. So increased pressure make it possible to store considerable more gaseous hydrogen in the same space. But in order to increase this pressure, a part of energy is consumed. And this pressure tactics, it is not linear. So if you go for 500 bar pressure, your volumetric energy density will not be doubled. So it's a non-linear curve. The pressure of 350 bar is used in the tank of gaseous hydrogen truck. For example, once with high zone, a loaded 55-ton truck need about 50 to 70 kg of hydrogen to travel 500 to 600 kilometers. At a pressure of 700 bar, the volumetric energy density of gaseous hydrogen is 40 kg per meter cube. The relatively high pressure is used among others for gaseous hydrogen passenger car, such as Hyundai Nexo, that is featured in recent block. Why? What is hydrogen used for? With a 125 liter tank containing only 5 kg of hydrogen, and it can drive about 600 kilometers. In liquid form and at a temperature of minus 252.9 degrees centigrade, hydrogen has a volumetric energy density of 71 kg per meter cube. Liquid hydrogen is also used as energy carrier for sustainable truck and aircraft, which are currently under development. This is giving you a perspective view of production and value chain of green hydrogen. So you see that left side, production is based on renewable energy sources and electrolysis. Then transport means of shipping, trucks or pipeline or a stationary storage in big tank, and then transformation. Without transformation, it can be feed into the industry, steel industry, chemical industry, or refinery. And with transformation, it can be fed to shipping, aviation industry, or it can be by synthetic fueling. It can use by these hard to abate sector. And then by converting hydrogen to green ammonia, it can be used for heating or power generation also. So this is the curve. This is showing volumetric versus gravimetric energy density of different gases. So when we are saying volumetric, then megajoule per liter, volume basis, what is the energy? And gravimetric, when we are saying weight basis, per kg basis, what the energy, megajoule, in megajoule. And you see clearly hydrogen comes here in extreme high value of gravimetric energy density. But volumetric energy density is quite poor. Whereas for diesel, biodiesel, and LPG and LNG, there we see that more volumetric energy density. So if we convert hydrogen to, ammonia or other biofuel or e-fuel, then we can get good energy density also, volumetric energy density also, and that's the need for aviation and marine sector and hard to abate sector. Here you can see that gravimetric energy density comparison, how it look like. So battery and then liquid fuel and gaseous fuel. So hydrogen is coming in this corner, but if you convert it to liquid fuel, then this can come in this region. So then we'll get the good gravimetric versus volumetric energy density. There are different type of hydrogen production model. We can use the full on-site production where all the renewable energy used for hydrogen generation, or a electricity from power grid where we are instead of renewable energy we are using the electricity from power grid, and we don't know whether it is renewable energy or it is a conventional energy sources based energy. Or we can use a hybrid model where we are having account of when we are feeding our electrolyzer plant with the renewable energy, and when we are feeding our electrolyzer plant by conventional energy sources. So advantage is that we can generate some certificates. So, and these certificates that can use by the industries and the users, and they can show their net contribution for carbon neutrality. And because renewable energy is used and it is accounted in this hydrogen generation, so that if one manufacturer who can own this whole value chain, then it's easy for having global recognizable certificates. So these are some model, and that's why our fuel, they prefer to have owning the full value chain. This is the hydrogen role in energy transition. So you can see that it can enable large scale efficiency renewable energy integration. Otherwise, if you are not having a hydrogen link, then you need to develop infrastructure for power line. And then, as you know, these renewable energy sources, they are located in remotely or in coastal line or away from cities. So, and our power line is already overloaded. So developing new infrastructure in power line, that will be a huge investment. Instead of, we can use some of this investment for developing green hydrogen based renewable energy network. So there we can convert the renewable energy to green hydrogen, and through pipeline or through distribution network we can distribute this hydrogen. And even it is possible that this hydrogen can be fed to the fuel cell, and or we can increase or decrease the consumption of electrolyzer plant or production rate of hydrogen, and in that way we can support the national grid stability. So we don't need to install um, costly battery energy storage system which Tesla is proposing for get rid of voltage fluctuation and good power quality, and then having stability of grid. And in US there is a huge investment on this side. So instead of battery megawatt gigawatt battery support, we can do this in a decentralized way by this hydrogen, green hydrogen, and it can help in energy transition. So this can be distribute energy across sector and region. You see that we are having this industry, we are having this marine sector, and we are having this chemical industry, and then act as buffer to increase system resilience. And that is the big role of green hydrogen based economy. So you get renewable energy, you convert it to hydrogen, then you use the fuel cell. So back you are having back converted it, and then when you are having any issue in the transmission line or power system, you can get rid of it by a local stabilizer unit. And these are the big sectors like transport sector, industry sector, and feedstock sector. And then heating, district heating, and building heating. We can use. It might be not a big application in India, of course it is in northern states, but it is very big application for Europe and America, where most of the countries or most of the part is in the seasonal time have facing a lot of cold. So this is an example showing the value chain of hydrogen. You see that renewable energy source, electrolyzer, and then you need desalinated seawater here, and then mobility sector, industry sector, and gas grid. These are the big consumers. So as we talk about, hydrogen is the new heavy duty fuel. It is 100% clean, and it is also reaching to the diesel parity. The technology is proven to commercialize green hydrogen. So what is in this value chain? Power generation, hydrogen production, hydrogen distribution, hydrogen station, and hydrogen fuel vehicle. And our company, we are looking on this part: hydrogen production, hydrogen distribution, and hydrogen station. We are also planning some activities for owning the renewable energy sources, and they are in research in hydrogen fuel vehicle. This is the complementary route to green transportation, how it is look like. It is very interesting slide, and it will give you that why we need to change the fuel type and how green hydrogen supports. So there is a fluctuation in wind, we convert it to hydrogen. So we can renewable energy directly where feasible without expensive grid upgrade. We directly use this renewable energy by grid, and it is for car and small truck buses. But the only prior condition is we must have stable grid, and we don't need any expensive grid upgrade, which is not the condition. If we want to convert all the, even in the US, if we convert all the cars into EV, electrical based car, then EV based car, then this infrastructure is not enough. It is supporting the growth rate, and it is customer are having a good experience in across Europe and US. Even in India also, in our national highways, they are equipped with these chargers. Slowly there is more penetration is coming, but issue is, if we don't, we cannot convert all the gasoline based car to electric EV car, because in order to do that we need to do the expensive grid upgrade. So what is the solution? We can do this by balance the grid via electrolysis, and use the hydrogen where feasible. So grid stabilizer is our electrolyzer plant, and then we use the hydrogen as a fuel, and it can fed to the car, buses, and trucks, and even in ferries and motorboats. And when we need for aviation and maritime, where this hydrogen cannot be a solution and EV is also not a solution, then we need to use this e-fuel, or we need to convert this green hydrogen to methanol, and this methanol can be used for as a liquid e-fuel for air and maritime. So what is the green hydrogen role in green stabilization? We talk about it. We can reduce or increase the hydrogen generation rate. So by that, we can reduce or increase the energy consumption in the electrolyzer plant, or we can schedule the electrolyzer operation with the national grid operator and grid availability. And within a short span of time, if for stability reason we need to reduce the consumption, we can do that. So if we are not depending only on the power grid or national power grid, we can develop our own green hydrogen based energy grid, and they will be complementary and supporting to each other, and that will be a win-win situation, because we are having redundancy in energy supply, as well as we need not to invest a lot of money on a technology which is not most efficient. So if we go for hydrogen based technology where we don't need any fossil fuel to run it, then it will be far efficient in terms of decarbonization journey. So for optimal investment in electrolysis and H2 storage capacity, allow for this value to be captured, given as exogenous market for H2 fuel. Through the utilization of H2 generation system, highly renewable system can reduce the cost to operate the grid, increase renewable integration into energy supply, and provide enough energy to fuel millions of fuel cell electrical vehicles at costs that are competitive with gasoline on a cent per mile basis. This is green hydrogen production correlation between levelized cost of hydrogen and operating hour of a grid connected electrolyzer. You can see that capital expenditure, it reduces as we increase the capacity, and operating expenditure little bit increased but almost constant. So we can see that wind share is from somewhere 90%, 85% to 60%, and we can see that optimal cost is based on the how many hour and with what capacity we are running it. So all in all, we can see that levelized cost is almost constant when we are running for more than 85% of capacity factor. And this table show you hydrogen weight versus volume at varying temperature and pressure. So for example, if you see that 25 degrees centigrade, if you are using this 1 bar, 0.1 megapascal, so this is 1 bar, you multiply by 10. So you see that 0.0183 kg per meter cube, but if you increase pressure to 100 bar, then it is 7.67, and if you increase to 300 bar, then it is 20.57537, and for 1000 bar, it is 49.424 at 25 degrees centigrade. And if you reduce the temperature, then this weight versus volume density is increased for the same range. For example, minus 25. you see this slightly change, and it is increased from 8 to 9, 50 to 55. So by reducing the temperature and by increasing the pressure, we can increase this volumetric energy density of hydrogen, and that is a crucial factor when we compare the efficiency of hydrogen, energy efficiency of hydrogen compared to fossil fuels. This is again green hydrogen product. You see the cost of when we are having fixed electricity cost, left one, and varying electricity, the fixed hydrogen cost and varying electricity price. So we see from 770 US dollar per kilowatt fixed cost to, if you reduce 200 US dollar per kilowatt, and we see that price difference of per kg of hydrogen is reduced, and then we need to run very less number of hours. Like normally, if you use this curve, this if electrolyzer system costs 770 US dollar, and you need to run in order to come into this price band, you need to run around 7,000 hours. But if your price for electrolyzer is only 200 US dollar per kilowatt, then you will come in this band very soon, and then it is some 1,600 hour, and it means that there is a lot of innovation is needed in innovation cost and in electrolyzer system cost. So new technologies and then cost-effective method. There are a lot of things are already done. Like we are not depending on now on platinum, costly platinum. We are using simple catalyst like nickel and others, and but it's still membrane and this technology and now excess heat. How to make use of this excess heat and how to make more efficient electrolyzers, and these are the questions. And here I think a lot of research is needed, and power electronics also play a big role. And on the right side, you see that when we assume electrolyzer cost is 200 US dollar per kilowatt, and but electricity cost, the previous curve is 20 US dollar per megawatt hour, but right one is it's varying from 10 to 40 US dollar per megawatt hour, and you see that the lowest price, then you see this price is within this band of $1 to $2 variation. So there are two ways. If we can reduce the system cost or equipment cost, or we can reduce the electricity price. This is power electronics enablers for green hydrogen. So you need to have those compressor technologies, you need to have electrolyzer technologies, and then you need to have this electrolyzer supply. This should be ripple free with the fast current control, and then efficient as much as possible. This is a model where wind solar based hydrogen production, how it works. So it needed big city locations. So we need to, it is a mapping, it is a model made for Europe. So this if you know that what are the big cities location, and if you know that what are the wind farm location, and then if you know that these big cities, when they curtail wind, so when they are not using these wind, when there is excessive production of energy, and then if you do have additional solar power and battery sources, then you can use this demand and supply model of hydrogen supply chain. So, and you can feed this hydrogen for annual energy demand by big cities bus fleet, for example buses, and hydrogen energy equivalent. So to run this bus fleet, how much energy is needed, and this energy is coming from the net balance from the big city location and available wind energy and available curtail wind as well as additional solar and power energy. And then you need to run top up with the grid electricity, and you need to run the optimal electrolyzer capacity at every wind farm. So this way we can input sources and consumers, and we can define exactly how much hydrogen is needed. Then we can schedule the operation of our electrolyzer plant, and we can run them either from fully from renewable energy or from the grid electricity, depending on the need. This slide is showing very interesting fact that green hydrogen or hydrogen as such, it is a very mature fuel for space travel. It is having TRL level 9, highest is 10. For industrial truck also, and stationary application also. But for aviation and shipping, there is a lot of effort is needed to bring it to the commercial part. So in order to bring it to the lower price and advance the TRL level, technology readiness level, a lot of research is need to be done. And there are some pilot projects where e-fuel is explored as a aviation fuel or shipping fuel. This is another view for showing you smart H2. You see that hydrogen generation is left side, right side is the hydrogen consumption. Left side is with the electrolyzer, and right side is with the fuel cell. Then you have factories, industries, you are feeding back to it, and then you are having smart fuel conversion. So you are feeding it, and this way, smart H2 storage. So one part is gone to smart fuel way, another part to fuel cell, and then third one is directly to the local heating. And by using this model and coupling this generation and consumption together, by knowing that how much is consumed in which sector, we can have a better plan for fuel value chain utilization. What are the future for smart H2? Hydrogen has the potential to fuel the economy while emitting little but clean water. We are at the leading edge of hydrogen revolution. The world finally tapped into hydrogen potential to play a key role in clean, secure, and affordable energy future. Fuel cell electric vehicles are powered by hydrogen and are more efficient than conventional internal combustion engine vehicle emission from petrol and diesel vehicle, include nitrogen dioxide, hydrocarbon, and particulate. These are a major source of air pollution, which is not happened with the hydrogen fuel cell electrical vehicle. And hydrogen power fuel cell electrical vehicle emit none of these harmful substances, only water vapor and warm air. As such, hydrogen is a real option for diversifying our transportation energy options while at the same time reducing pollution. These are so you can see it that in Copenhagen, our fuel is feeding a fleet of taxis. So all the taxis, a couple of hundred taxis, they are fed by our fuel. And similarly, in other part of Europe, this is like in Ireland, you see these buses, green hydrogen buses are reality. So what need to be done? We need to increase the penetration of intermittent and zero carbon generation sources, increasing the stock of fuel electrical vehicle, creating reliable long-term demand, and subsidizing capital investment in energy storage project. So focusing on these three rudiments: zero carbon generation, increase stock of FCV, and subsidized capital energy storage project. This will help to establish an environment to favorable for a more market-driven shift in energy management. And high penetration of intermittent renewables provide a surplus of zero marginal cost generation that can be leveraged to generate hydrogen at a competitive price to other fuel. And being said that, I will come to the conclusion that we have talked about global mega trend, green energy shift. We talk about innovation in green hydrogen technologies, and then we also discuss harnessing advantage of full value chain of green hydrogen energies, essential practice. So now I will close my talk and open the forum for any discussion. So time for your questions.
Any question from the audience?
I cannot hear.
Good afternoon, sir. My name is Visham Babu, research scholar from NIT Manipur.
Dr. Kundar, are you speaking? I can't hear you.
Yes, sir. Yes, sir. Last one of the audience was speaking, but I did.
Type in that also possible.
Okay, we'll see. Otherwise, I will allow you.
They can type on chat and I can see it. I can reply. I had a question. Is it possible to have negative carbon? Yes, and it is possible. Negative carbon means you need to either you need to capture the carbon from the environment and store it, or you need to use a fuel which is for example, in certain application methane is needed, and there you use the green hydrogen, convert it to green methane, and then whatever the resulting carbon Yeah, this question regarding Bhutan, that is having different model. In Bhutan, there are more greenery and environment, and they are respecting Mother Nature a lot. So they are not using fossil fuels. There are a lot of energy that is coming from hydropower, as well as there are more this carbon footprint, which is negative, that is coming from the greenery and the forestry. So that is there. But if you talk about conventional fuel and replacements of conventional fuel and getting it carbon negativity, then you need to capture the carbon, generated carbon. That's the only way. Any other question?
Hello, sir. Using hydrogen fuel in place.
You mean hydrogen car per kg hydrogen carbon? Fuel cell and hydrogen part. So we are having the motor and drive, EV and this hydrogen vehicle. They both will have the same. When you come to the fuel cell and hydrogen, and efficiency of this hydrogen and fuel cell, that is around 70%, and then back renewable energy to hydrogen, that is also 70%. So this is 50% from renewable energy to feeding through your inverter. So yes, 50%. So you mean hydrogen generation, that we must have such a good infrastructure that we can compensate this loss. So if you compare one to one, apple to apple, then this loss in renewable energy to hydrogen and back conversion from hydrogen to electricity, or supply to the inverter in EV, that loss we need to compare. And because in one case we are directly feeding renewable for example battery, we are taking directly the energy. But if you compare that all the EV should be run by renewable energy, you make sure that it is running by renewable energy. In that case, we are already competitive, because that is not possible. In case you want to run the EV by renewable energy sources, that is not possible with present infrastructure. Are you with me? So, in terms of efficiency and those calculation with electricity calculation, then it is we need to compensate. Either we need to increase the efficiency of fuel cell, and we need to increase the efficiency of electrolyzer, or we need to or a whole solution should be cheaper than this battery based solution. So what is the cost involved in the battery, what is the cost involved in electrolyzer and fuel cell, that should be equal, and that is not possible now, because there is a lot of technology cost. And in terms of per kg rate of hydrogen, if you look on it, then right now it is depending on $6 to maybe $15, depending on the location and depending on how far this hydrogen source is and what type of transportation is used. And this should be reduced to $1 to $2 value in order to keep it commercial viable. And so government are giving a lot of subsidy nowadays, but the price is still higher.
Thank you so much.
You are welcome. And then I should finally say you thank you for inviting me for this
Just a
talk.
minute.
Okay, thanks.
Thank you, sir, for your valuable speech. So now we will be having a short tea break, and then we will be having technical session from 3:30 p.m. So I request all of you to be back here at 3:30 p.m. And also at 5:30 we will be having certificate distribution session and valedictory function. So for that I request all of you to be there.